So today we're going to look through exactly what is a linear equation. And we're going to look at different types of linear equations. You've probably seen a lot of this before. It's just definitions is what we're looking at today. So first I want to look at what a linear equation actually is. So a linear equation in the variables, we'll call them x1 through xn. So x1, x2, x3, all the way up to xn. So you've got n different variables here. It's like saying x, y, z, that's 3 variables. So we've got n variables here. And a linear equation in those variables is just an equation of the form, I'm going to call it a1, x1 plus a2, x2, all the way up to an, xn is equal to b. So here we're just taking a linear combination, as we'll see later on, a linear combination of x1 through xn. So it's a constant a1 times x1 plus a constant a2 times x2. And you go all the way through till you get to an, xn, and then it equals another constant b. So each one of the ai's is a constant. Okay, and b is a constant. So any equation of this form is called a linear equation. There are no squareds, cubes, etc. Each variable is only to the power 1. Okay. Now, we're going to deal with systems of linear equations in this class. That's basically what the whole class is about. So we're going to look at systems of equations of this form. Okay. And we're going to look at solving them, different solutions. Can they be solved? Can they not be solved? Etc. Okay, and we're going to look at different methods of doing that. And you know this from probably back in middle school when you did this. You can solve these equations simultaneously. So you probably did it before when you looked at, let's say, I don't know, I have no idea if this one will actually work out or not. But we won't solve it. I'm just going to write it down to show you an example. Let's say we had those two equations. Okay, that's a system of linear equations in the two variables x1 and x2. You could go ahead and solve them at the same time to see the x1 and x2 that satisfies both of those equations. Okay. When you only have two variables, a method that they tend to use is to do this graphically, which is to actually plot the two lines. So you could write them in the form y is equal to mx plus b, or in this case you could write them in the form x2 is equal to mx1 plus b. Okay, so you're going to write each of these equations in this form, find what the slope m is and what the y-intercept b is. Just as a heads up, these two b's are not the same. Don't get confused here. All I'm saying is you're just going to rewrite it in the way of drawing a line. So you're going to write it in the form y is equal to mx plus b. And then once you've done that for each of your two equations, you can plot them on an xy plane and you can see if they cross. Okay, if they do cross, okay, so if you end up plotting these two on an xy plane and you end up, let's say, I have no idea what they'll come out as, but let's say that they come out with something like this. Okay, if you get your system of equations only crosses at one point, okay, this system is said to have a unique solution. So if it crosses at one point, then the system has a unique solution. And that solution is just the x1 and x2 values at that point. Okay, with this being the x1 plane and this being the x2 plane. Okay, so that point where they cross is the solution to the system, x1 and x2. Sometimes you may get a system of equations where they are parallel. So you're going to plot these two lines and you find that they are parallel. Okay. What actually happens in this case, it means that the left-hand sides of the equations are scalar multiples of one another, but the right-hand sides of the equations are not. So if we come back here, it would mean that the left-hand sides of these equations would actually just be scalar multiples of one another. So you could have 2x1 plus 3x2, and then 4x1 plus 6x2. Okay, so your left-hand sides are multiples of one another, but most importantly, your right-hand sides are not the scalar multiples of one another. So they could be 5 and -3 in this case. Okay, so when your left-hand sides of the equations are scalar multiples of one another, but your right-hand sides of the equations are not, you will end up with two parallel lines. In that case, they never cross. Because they never intersect, there is no x1 and x2 value that satisfies both of those equations. So therefore, there is no solution. So when the lines are parallel, it means that there is no solution. Remember, that happens when the left-hand side of the equations are scalar multiples of one another and the right-hand sides are not. The other thing you can also find is where they actually intersect at every single point. So you could end up with one line like this, but then you draw the second equation and it comes out with the same line. In that case, they are basically the same equation because they give you the same line. Coming back to what I said before with those parallel lines, we said that the parallel lines happen when you have the left-hand sides are scalar multiples of one another, but the right-hand sides are not. In this case, where you get the same line, it must mean that both the left-hand side and the right-hand sides of both equations are scalar multiples of one another, and we'll look at an example of that in a second. But this would mean that they intersect at every point. So they must have infinitely many solutions. So any x1 and x2 that lies on that line, for example, this point here or this point here, the x1, x2 values at those points must be solutions to the equation. Well, there's infinitely many points that lie on a line. So you must have infinitely many solutions. Okay. So what we can see here, there's three different possibilities that we have. They either intersect at exactly one point, so there is one unique solution to our system of equations, or they can be parallel lines, which means that they never intersect, so there is no solution to our system of equations, or they can intersect at every single point because they're basically the same line, which means that you have infinitely many solutions. So we can have one solution, no solutions, or infinitely many solutions. You can't have, let's say, just 3 solutions to a set of equations, okay? System of linear equations is never going to have a set number of solutions. It's either one, none, or infinitely many. Okay, so keep that in mind. A couple of examples of this that I'll quickly run through. Okay, first one, x1 minus 2x2 is -1, and -x1 plus 3x2 is equal to 3. Now, you can do this one of two ways. You can either go ahead and solve these simultaneously mathematically, or you could go ahead and draw them out. If you wanted to use Desmos or your graphing calculator, you can absolutely do that. But you would find that these two lines actually only intersect at one point. And because they only intersect at one point, and I'll tell you what the point is so that you can go ahead if you tried this out, they intersect at 3, 2. So they only have one unique solution. Okay. Another example. Okay. We have 2 equations here in 2 unknowns, and if we look at the left hand sides of the equations, The second equation on the left-hand side is just a multiple of -1 of the left-hand side of the first equation. So if I took this left-hand side and multiplied it by -1, I would get the left-hand side of my second equation. But my right-hand sides, if I multiply -1 by -1, I don't get 3. So my left-hand sides are multiples of one another, my right-hand sides are not. So therefore there is no solution to this system of equations because they're going to end up being parallel lines if you were to graph them. Okay. Third example. In this case, we see that both the left and the right-hand sides are scalar multiples of one another. So if I take the whole first equation, both left and right-hand sides, and multiply it by -1, I end up with my second equation. So there are infinitely many solutions to this system. There are infinitely many x1 and x2s that satisfy this equation, or this system of equations. So you'll see that everything we've done so far has just been a system of two linear equations with two unknowns. Okay. As we go throughout this, we are going to deal with larger systems. I probably won't give you anything larger than having 5 variables in it. Okay, so you may end up with something with 5 equations and 5 unknowns, something like that, but I probably wouldn't give you anything larger than that. But this is a good way of just looking at it in terms of like small scale, looking at 2 equations in 2 unknowns. What we're going to do as we progress through the next week or two is actually deal with these systems written as matrices. Okay, hopefully most of you have seen matrices before. But what a matrix is just an array of numbers. It's a way of writing a whole set of numbers into an array. So, for example, let's come back here to one of the equations that I did here. Let's say I've got 2x1 plus 3x2 is equal to 5. 3x1 plus 4x2 is equal to -3. And I wanted to write that in matrix format. Again, we're going to deal with this later on again, but just to kind of give you a taste of what's coming up. What you can do is actually write this system of equations in matrix format. And the way that you do that is to take the coefficients of my variables in both of the equations and write them in a matrix. So I have 2x1, 3x2, and then I have 3x1 and 4x2. So if I were to write that in a matrix, I'm going to have 2x1, 3x2, and 3x1, and 4x2. So I write my coefficients of my variables from the equations in a matrix. I now have my matrix, my array of numbers. Then if you've done some matrix work before, you'll know that the way that you actually multiply matrices, and we will go through this later on for those of you that haven't seen this, is you multiply across and down. So if I multiply across and down here, I'm going to get 2x1 plus 3x2. Same thing here. When I multiply matrices, I multiply across and down. So I'm going to get 3x1 plus 4x2. Okay? So I can write this system of equations as an array of numbers, as matrix format. So I can then let that equal, I think I had it equal to 5. And I think it was -3. Okay, so you can write these systems of equations in such a way that you can write it as an array of numbers, as a matrix. What we actually end up doing is forming a matrix by taking this matrix here and this matrix here and putting them together to form another matrix. And we're going to perform stuff on that matrix in order to find the solution to this system of equations. That's what we're going to do throughout the first couple weeks. But I'm not going to go through all of that now. We will go through that in class starting on Tuesday. but just be aware that that is kind of where we're heading and where matrices come into play here. What I'm going to do now is actually just go through this the long way and try and solve a system of 3 equations in 3 unknowns by doing this by hand, but I'm going to be using the same kind of operations that I use on the matrices here. Okay, so then that way you can kind of get a feel for what's coming up. Okay, so let's say I've got x1 minus 2x2 plus x3 is equal to 0. 2x1 plus x2 minus 3x3 is equal to 5. 4x1 minus 7x2 plus x3 is negative 1. Okay. What I want to do here is solve this. I want to find x1, x2 and x3 such that they satisfy all 3 of these equations. Okay. The way that you actually do this is by elimination of variables below the equation that you start with. Okay, so let me go through that. What you want to do is eliminate x1 from every equation except for the first equation. Then you want to eliminate x2 from every equation except for the second equation. Then you want to eliminate x3 from every equation except for the third equation. Okay, so then what you should end up with is x1 in the first equation is equal to something. x2 in my second equation is equal to something. And x3 in my third equation is equal to something. So I need to start with x1 and eliminate it from every single equation except for the first one. Okay, you're going to do this, and just as a tip here, and this is going to work the same in matrix format, you're going to work top down, then bottom up. Okay, what do I mean by that? I want to work top down. So I'm going to eliminate x1 from the second and third equations. Once I have done that, I'm not going to have x1 anywhere except for in my first equation. Okay? Then I've got x2 in my second equation. I want x2 in my second equation. But I know that that is the only place that I want it. But right now I am working top down. So once I've got x2 here in my second equation, I want to eliminate x2 everywhere below that second equation. Okay, so you're going to work from the top down. Then at the end, I'm going to work bottom up. So I can then eliminate x2 from the first equation and eliminate x3 from the first and second equation when I work bottom up. But right now I want to work top down. So I'm going to eliminate x1 from my second and third equations. How do I do that? Well, if I take my first equation, multiply it by 2, I'm going to end up with a 2x1 here. Then what I can do is say take my second equation and subtract my first equation from it when it has been multiplied by 2. So if I take equation 2 and subtract 2 of equation 1, okay, that's going to give me 2x1 plus x2 minus 3x3 is equal to 5, and I'm going to subtract 2x1 minus 4x2 plus 2x3 is equal to 0. So I've taken my first equation, multiplied it by 2, and I'm going to subtract that from that second equation. When you do that, I'm going to end up with no x1s, because 2x1 minus 2x1 is 0. Then x2 minus negative 4x2 gives me 5x2. And then negative 3x3 minus 2x2 is negative 5x3. And then 5 minus 0 is 5. So I am now going to replace my second equation with what I have found here. So I've taken my second equation And I have found a way to eliminate that x1 variable from my second equation. So I've taken my second equation, subtracted 2 times my first equation from it. It's eliminated that x1 variable, and I'm just left with 5x2 minus 5x3 is equal to 5. Okay. Now let's look at the third equation. I want to get rid of x1 from my third equation. I need to only have x1 in my first equation. So I'm going to do equation 3 minus how many multiples of my first equation? Well, I've got a 4x1 here, and I know I need to get rid of x1. So I'm going to subtract 4 times my first equation from it. So I get 4x1 minus 7x2 plus x3 is equal to 1, or negative 1. I'm going to subtract 4 times my first equation. Okay. If you work that out, again, I'm not going to have any x1s left. Okay, so there's no x1s left. Then negative 7 minus negative 8x2 is going to leave me with x2. Then I'm going to have x3 minus 4x3 is going to give me negative 3x3. And that's going to equal negative 1. Okay, so now my system of equations, I've still got x1 in my first equation. Okay, but I'm now replacing my second equation with 5x2 minus 5x3 is equal to 5. And then my third equation gets replaced by x2 minus 3x3 is negative 1. Okay, so I've eliminated x1 from everywhere except for in my first equation. x1 now only exists in one equation. Okay, now I need to eliminate x2 from my third equation. Remember, I'm working top down, so I'll eliminate this x2 later on. But right now I need to leave x2 in my second equation but eliminate it from my third equation. Okay, so a couple of ways that you can do this. Right now you have 5x2 here. Okay, the order that your equations are in when they have the same variables in them, so you don't want to start switching the first equation with the third equation here because you've already eliminated x1 from this third equation. But these two equations, I could switch them around if I wanted to. That way I've got an x2, just an x2, in my second equation position where I want an x2 to be. So I could do that. Alternatively, what I could do is divide this whole equation through by 5. Okay, so let's do that, because again, I can do that without leaving fractions or decimals anywhere, but it will give me just x2 in that second position in my second equation. So I'm going to have x1 minus 2x2 plus x3 is equal to 0. Then I'll divide that second equation through by 5. It's going to give me x2 minus x3 is 1. And my third equation is that. Okay. Now I want to eliminate x2 from my third equation. If I want to do that, all I have to do is do my third equation minus my second equation, because then I'll get x2 minus x2, leaving me with no x2s. Then I'll get negative 3x3 minus negative x3 is going to leave me with negative 2x3, and then negative 1 minus 1 is going to leave me with negative 2. So let's write that down. I'm going to have x2 minus 3x3 negative 1, x2 minus x3 is 1, and I'm going to subtract them. Okay, and that's going to leave me with negative 2x3, and that's going to leave me with negative 2. Okay, so my system is now x1 minus 2x2 plus x3 is 0. Then I've got x2 minus x3 is equal to 1. And then we came up with this new equation here, which is negative 2x3 is equal to negative 2. Okay. Again, I want x3 in my third equation. Right now I've got a multiple of x3. So what I'm going to do is just divide that through by negative 2. And that'll leave me with x3 is equal to 1. Okay, so I have now worked top down. I've eliminated x1 from every equation below the first equation. I've eliminated x2 from every equation below the second equation. Okay, and I've only got 3 equations, so I can't eliminate x3 below the third equation. Okay, but I now have x1, x2, x3. But now I need to work bottom up. So I've worked top down. Now I need to work bottom up. So I'm going to eliminate x3 from my first and second equations. Okay, so all I have to do there is just say, okay, I'm going to take my first equation and subtract my third equation. And I'm going to take my second equation and add my third equation. You may have to add or subtract a multiple of that third equation if I were to have, let's say, like a 2x3 or a 3x3 in my first or second equations. Okay, but if you go ahead and do that, you're going to end up with x1 minus 2x2 is negative 1. And I'm going to get x2 is equal to 2. And I'm going to have x3 is equal to 1. I'm going to move that over just so that we can see what is happening here. Okay. So I've eliminated x3 from my first and second equations. The only thing I have left to do now is to eliminate x2 from my first equation, again working bottom up. So if you do that, I can take my first equation, E1, and I can add 2 times my second equation. If I do that, I'm going to get the negative 2x2 here, plus the 2x2 from my second equation. It will eliminate the x2 from my first equation. So I'm going to get x1 at the end is equal to 3, x2 is equal to 2, and x3 is equal to 1, if you were to do that. Okay. I would encourage you to go back and look at what we have just done, because this is not a simple thing to kind of grasp, but we will be doing it constantly over the next 2 weeks. So this is not the only time you will see this, and I will go through it again in class because I know it is not easy to grasp. But the main thing to remember is we have worked top down and then bottom up, leaving x1 in the first equation, x2 in the second equation, and x3 in the third equation. Okay, so we have worked top down to eliminate x1 from the second and third equation and to eliminate x2 from the third equation. And then we have worked bottom up to eliminate x3 from the first and second equations and to eliminate x2 from that first equation. And that way we have solved 3 equations in 3 unknowns. Okay, so I would encourage you to go back and look at what we have just done to see if you can kind of grasp the concept of adding and subtracting multiples of these equations from one another. On that note, something that I want to quickly mention is elementary row operations. Okay, there are 3 things that I want you to know. Okay. Replacement, interchange, and scaling. Okay. These are the 3 things that you can do to these equations that are not going to affect its solution, but will help you solve them. Okay. First one is replacement. What I have done back here when I have solved these equations, each time, let's take this one here for example, my first thing that I did, I said I wanted to eliminate x1 from my second equation. So I took my second equation and I subtracted 2 times my first equation from it. Okay, and I have replaced my second equation with my solution. So I've added or subtracted a multiple of one equation from another and then replaced an equation with that solution of adding or subtracting a multiple from it. Okay, so you can replace an equation by the sum of itself and the multiple of another equation. Okay, that does not change the structure of our system whatsoever. Okay, adding and subtracting multiples of equations from one another within that system does not change its structure and does not change its solution. Okay, if you need proof of this, just go through a quick 2x2 example where you've got 2 equations and 2 unknowns. When you go ahead and solve that algebraically, that is how you solve it. You add and subtract multiples of one from the other. Okay, or you substitute in, which is the same idea. Okay, so replacing an equation by the sum of itself and a multiple of another equation does not change its structure and helps you find that solution. In the same way, interchanging 2 equations. Let's come back here. Okay, what I did here at this point over here was I divided my second equation by 5. Okay, we'll go through that in a second with scaling. But what I could have done, as I said before, is just switch these 2 equations around. Does that change my structure of my system? No. Okay, it helps me solve it. I wouldn't recommend interchanging 2 equations, let's say like first and third, because then you're going to end up with x1 in your third equation and not your first. So do this sparingly, but if you do need to switch 2 things around and it helps you solve it, that's totally fine. It does not change the structure of our system and can help us solve the system of equations. So I can interchange any 2 equations, but again, bear in mind what you are actually aiming to do, and I wouldn't interchange 2 equations that's actually going to hinder you from solving. Okay. And as I just said, at one point there, I divided a whole equation through by 5. Okay, that's scaling. Okay, as long as whatever I do to one side of the equation, I do to the other. So I divided that whole equation through by 5. I didn't just divide the left-hand side or the right-hand side by 5. I divided the whole equation through by 5. I've scaled it back by a multiple of 5. That doesn't change the structure of my system. It doesn't change the solution. Okay, it's just the same equation as you would see if it had 2 variables, 2 unknowns. We said that it would be the same straight line. Okay, so because it is the same line, scaling does not do anything to it. So scaling is when you multiply or divide both sides of an equation by a scalar. Okay, none of these 3 things change the system, but they help you solve. Okay, we're going to go through, you're going to see these 3 things come up time and time again over the next couple of weeks as we actually solve these systems using matrices instead. And instead of actually doing this to equations, you're going to do this to rows of a matrix, and it actually makes it way easier to keep track of what's going on rather than dealing with all the variables thrown in there as well. So we will go through this again, and then we'll look at how to simplify it using matrices. But these 3 things help you solve a system of equations, and they keep that system of equations the same. Okay, they just help you solve the actual system. Okay. 2 more definitions I want to go through is consistent and inconsistent. A linear system is consistent if it has at least one solution. That means it either has one unique solution or it has infinitely many solutions. In either of those cases, this system is said to be consistent. So as long as you can find one solution to the system of equations, it's consistent. A linear system is inconsistent if it has no solutions. So it's just another way, another definition, another way to describe what's going on if you have one or infinitely many solutions or no solutions. It's just another word for it. Okay. If you go to the class notes from today, they are online on Blackboard under class notes. It will lead you to a Google Drive that has the notes on it. If you look at the ones from today, I have put an extra example in my notes that looks at an inconsistent system and what you actually come across. We will deal with this more when we look at matrices, but what you will see on that example, it's on the very last page, right at the top of the last page of today's notes. It goes through this system, 3 equations in 3 variables, and it goes through exactly the same as what we did back here. Okay, gives you 3 equations in 3 unknowns. It eliminates x1 from the second and third equations. It then eliminates x2 from the third equation, so it's worked top to bottom, top down. Okay, when you got to the bottom of this one, you actually find that you end up on your third equation with 0 is equal to 1. You don't actually end up with any x3 terms whatsoever in your third equation. You don't end up with any variables whatsoever in your third equation. It's just 0 is equal to 1. That, of course, is not true. We know that about math. 0 does not equal 1. And because of that, it has no solutions. So an example of this, if you go to my notes, it is on the 4th page of my notes from today, and it's the first example on the 4th page. So I would encourage you, once you've looked through this example again and kind of figured out like the methodology of it, of working from top to bottom and then bottom to top to eliminate x1, x2 and x3 from the appropriate equations, once you have done that, then go and look at this example and you'll see that you hit a point where it says 0 is equal to 1. Well, of course, that can't be true ever. So we know that this system is not consistent. It's an inconsistent system because it has no solutions, because you cannot possibly have that when you solve a system of equations. Okay. If you have any questions about this, please feel free to email me, call me, or text me. Or you can ask in class tomorrow. I will do a quick recap at the start of class.